what do you get when you integrate the rate of change of a function? I have an example here. I have P of t represents the population growth rate for some population of people, say, and it's in people per year. So all right, if the rate of change of the population of something is 100 people per year for, say, 20 years, I might ask, what is the total change in the number of people from t is 0 to t is 20? And then you would just think, okay, rate times time, at 100 people per year times 20 years, that's going to be 2,000 people. And it's kind of like the area, right? Just the base times height, finding the area. But what if instead of being a constant rate, the rate of change of population is something more complicated? If there's like booms and declines in the rates of change. How can you figure out what the change in population is there? Well, what you would do is you would partition the axis here, and you could approximate the rate on all these little subintervals by using the heights of these rectangles here. And in so doing, so you'd say like base times height, base times height, base times height for pretty much smaller versions of what we just did, and then you would add up all these changes in population, get the total change, and you would get a more accurate representation by doing an integral. And that's what it actually is. The total change in population for for any function that you get would be the integral of P of t dt from wherever it is to wherever it is that you're interested in. Generally speaking, this is what happens when you integrate a rate of change. What you get is, all right, if you integrate the derivative of something, what you wind up with is the total accumulated change in the quantity that the thing is measuring. So for example, if you integrate a rate of change of population, what you're going to get is total population change. If you integrate an acceleration, you'll get total change in velocity. So functions that are, integrating rates of change, that you get an accumulation of something. Or you could also get like a deficit. That would also, the concept carries over too if there's a gain or a loss of something, right? The accumulated change up and down is what you get from doing a definite integral. You can also carry that over to something that's not directly a rate. An example of that is if you have a linear density function of something, say that you have a rod whose density varies from point to point. How is density measured? It could be a linear density, it could be in, say, kilograms per meter. So let's say that this is our function here, right? So the rod is really dense here and less dense here and it's less dense here, right? What you get if you integrated this function, the integral of delta x dx, from 0 to a, say, if that's a, what would that be? Well, you would look at the units and you would get kilograms per meter times meters, and this thing would represent the total mass. But again, it's like an accumulation of mass over the entire thing. So it doesn't always have to be a rate of time per se, but those are the easiest ones to see. Generally speaking, right, when you integrate a rate, I said what you get is the total accumulated change, which is, this is like mathematical shorthand for writing that. You get the one, right, the value of the function at the end point minus the value of the function at the beginning. You can rearrange this if you make a little substitution here, change b for t, and then if you bring this over to the other side, what you will get is, you get the value of the function equals the initial value plus the change from a to t of f of x dx. It says that a function can be represented by some initial value plus the change undergone by that function from that initial value to some point t. We're going to use this in this example over here. You want to come in here. I got a word problem. Little thing. I whipped up a storage tank. You have a tank that's full of, it holds 300 gallons of water, and it's leaking out at the variable rate, 20 minus t gallons per minute. So the rate at which water is leaking out is decreasing because this is a decreasing function, right? At first, it starts out, it's leaking out at 20 gallons per minute, and then as time goes on, this number falls, where ultimately at t is 20, it stops leaking out. Question that I might ask is, well, how much water leaks out between the 10th and 20th minutes? Well, that's easy. All you have to do is, you know that what you get when you integrate a rate of change, you get the total amount that changed. So how much water leaked out would just be the integral from 10 to 20 of 20 minus t, dt. And you can carry that out. Let's see what this is. You get 20t minus 1/2 t squared. And when you evaluate that from 10 to 20, what you'll wind up getting, if memory serves, is a total of 50 gallons leaked out between the 10th and the 20th minutes. So just interpreting this integral as the total number of gallons. This thing here, how much water is in the tank after the full 20 minutes? Now this is what's going to be like this over here. You want to come back over here, right? The total number of gallons is the initial plus the change. So it's going to be the initial 300 gallons minus, because it's leaking out, the integral from 0 to 20 of 20 minus t dt. I'm not going to, well, I could evaluate this. This would be 300 minus, and when you carry out this integration, what you'll get is 20t minus 1/2 t squared, evaluated from 0 to 20. When you plug in 20, what do you get? You get 400 minus 200, which is 200, so you get 100 gallons in the end, right? Because when you plug in 0, it goes away. Okay, finally, what is the function that actually represents the amount of water in the tank? You can interpret this in two ways. You don't know what the function is, but you can find it because you know its derivative, the rate of change of the number of gallons, is 20 minus t. So you could look at this as an initial value problem, like v prime of t is 20 minus t, with the initial condition v of 0 is 300, right? Here's the rate of change, here's the initial value, and you could solve this like you would any other initial value problem. The way to do it is to write it as a function defined by an integral, right? The volume in the tank at time t, v of t. Again, initial plus change. It's going to be the 300 plus the change, which is the integral from 0 to t of 20, not 20 minus t, because we already used t for the variable here, so 20 minus x dx. You see that this function satisfies these two conditions. If you differentiate this, you do indeed get 20 minus t from the second fundamental theorem, and if you plug in 0, you get 300.